Good morning, everybody. Are you able to hear me?
Yes, we can hear you.
Okay, great. Do you have any echoes or is it fine, the audio? Okay, thanks. So let me first share my screen. Okay, fine. So recollect that during the last class that we had, the afternoon session on Monday, we ventured into a new aspect that we had not looked at earlier on. So if you're looking at, let's say, the way we have been approaching this particular problem, there are four aspects to it. So first of all, we took up the simplest thing that we can have, which is a zero size, by which we meant the particle. And we looked at the description of the motion. Which we called as the kinematics. And that's something that we completed with the morning session day before yesterday. So that's pretty much done, right? Next, we looked at going from the particle, which is more of an idealization, to what we called as the rigid body, though we know very well that the eventual structures that we are going to be interested in are flexible body. This is at least going from a zero size to a finite size. And once again, we dealt with kinematics over there. And in particular, we introduced the concepts of angular, let's say, first velocity, which we denoted by omega. I just want to make sure that all of you call this as omega, which is, as you know, a Greek letter in the Greek alphabet. Uh, it does look very similar to the English letter W, but W is typically reserved for one component or measure number of the velocity. So omega is what we use for the angular velocity. So when you talk about this as while presenting your homework, I would like to ensure that none of you call this as a W, but as a omega, right? Similarly, we also introduced the concept of angular acceleration, which is alpha. And neither of these, I would like to re-stress, re-emphasize that neither of these were necessary or had any meaning whatsoever when we were looking at the particle, because the particle is zero size, and when you have a zero size, it's essentially a point. In fact, a massless point, because we were not even looking at the kinetics over there. And therefore, it really didn't matter whether it had a mass or not. But a rotation of a point doesn't have any meaning. So this is something to emphasize and remember. So which is why angular velocity or angular acceleration also had no meaning. But nonetheless, we did look at curvilinear coordinates. So if you remember what we did over there, we did look at various coordinate systems, not only Cartesian, but also the curvilinear, in which we had two kinds. One is the polar or cylindrical, depending upon whether it is 2D or 3D. And then we also looked at the natural or intrinsic, which again, depending upon whether it's a planar curve or a 3D spatial curve, can be tackled with and without, or without and with the torsion, respectively. Right now, the curves that we are talking about there are very different from the angles that we are talking about here. So what we are dealing with over here is essentially these two quantities are helping us understand theta, which is the rotation. Okay. And this is very different from what we were trying to do over there, where we were looking at a curved path. Okay. So it's the path which was getting curved. The point or the particle was not actually rotating because it has absolutely no meaning. It just doesn't have a mathematical equivalent. In fact, even when we go to a line, for that matter, we can think of a line rotating this way, a line rotating this way towards you and me, but we can't think of a line rotating about its own axis. Okay. There are certain branches like structural mechanics where we do finite element analysis and we introduce fictitiously what is known as a drilling degree of freedom. As you know, drilling is a manufacturing process where you bring in holes into a structure. But those are finite diameter, whereas a line, when you talk about it, just like a point is zero size in all directions, a line has a finite measure only in one direction, which is its length. It has no thickness, it has no width, right? So that is something that you ought to remember, that these are two aspects which sound similar and can confuse beginners in dynamics, that you're talking of a curved path there and we're talking of a rotation here. No, the rotation is of the body. Okay, it can be at the same location and rotate, just like your aircraft over here can have a pitch, it can have a yaw, it can have a roll. Of course, a fixed wing aircraft cannot stay still, but if you had an helicopter, for example, it could be hovering, and while it's hovering, it could do a pitch, it could do a roll, or it could do a yaw, right? So, in other words, it's not necessary for motion to take place even in a straight line, leave alone a curvilinear path, to talk about rotations. Okay, so rotation is something that is happening to the body, whereas the curved path traversal is essentially happening for a point in the body. And it could, of course, in general, it does happen for all points of the body, but it could happen in different ways for each point. And therefore, we never talk of the, let's say, the translation of the aircraft as a whole. We talk of the translation of a point in the aircraft, and we typically talk of the translation of the center of mass of the aircraft. Which we will introduce as a concept today, because we are going to venture into, after finishing a few more aspects that we will cover today. So we will cover a few more aspects of the rigid body kinematics. We are not yet done with it. So the first half of today will essentially be about that, to bring to a closure all of kinematics, because we are done already with particle kinematics. That is already done entirely. And now rigid body kinematics is something that we will complete today. Once we are done with that, we will venture into the third aspect, which is not just the description of motion, but the causation of motion, which, as you might recollect, we introduced just as the terminology earlier, namely the kinetics. Okay. And which is where we will invoke two kinds of laws. One is associated with particles. The other is associated with rigid bodies specifically, right? But the one which is associated with particles, we will extend it to the point that we identify as a replica or representative of the rigid body, namely the center of mass. So, what are the things that we will deal with in terms of the kinetics is something that we will see shortly. But essentially, whatever we are doing in dynamics, be it kinematics or kinetics, is going from the cause to the effect. Okay, whether you're doing it knowingly or unknowingly is a different matter, but essentially, you're looking at going from a cause to an effect. Okay. The cause is, of course, a force, which in a more generalized sense, we can call include moments as well. And the effect is, of course, a translation, which we will denote by U, and the rotation, concepts of which we have introduced since the last class. Now, in general, for problems, especially those involving aircraft, these are all three-dimensional vectors. In other words, if it's a Cartesian coordinate system, they would have I, j, k hatted terms, all of which are non-zero in general, right? Now, when we have a certain set of forces and a certain set of moments, and we want to determine what is the displacement, that displacement that we are talking about here is of a point always. And if it is a rigid body, it would be, let's say, the center of mass. It could be any other point on the rigid body, but this is usually convenient to work with, and we will see why once we introduce that concept, or actually reintroduce, because pretty much every one of you will be familiar with center of mass from your school physics. So now that is what we looked at, and that is very similar to the displacement of any particle. So it's not very different from particle kinematics. Where the difference does come, of course, is in terms of the rotation. Okay. The rotation is, of course, of the rigid body, which in my slides, as well as when I write on the blackboard over here, I'll be calling it as RB, abbreviating it as RB. Okay. And whenever I say RBD, essentially it means the rigid body dynamics that we're talking about. Now, there are two aspects to it, the displacement and the rotation, and each of them have a specific cause, which is the force and the moment that we introduced over here. So the resultant forces and the resultant moments. Okay. Now, while the force is acting at a point, the moment is essentially about a particular axis. Okay, so okay, so for example, uh, if I want to roll, then I obviously deflect my ailerons in a differential manner on the starboard and the port. One of them goes up, the other goes down, and essentially I increase the lift on one and decrease the lift on the other, and essentially a roll is encountered. So that one component of theta is what we are getting by one applying one component of m that we see. Okay. Similarly, of course, the pitch where we deflect the aileron, and the rudder when we deflect when we deflect the rudder, we get a yaw, right? So these are the three rotations and three moments associated with it that we are familiar from aircraft parlance. But whatever we do is, of course, generally applicable for any rigid body whatsoever. Now, while our interest is in going from this cause to the effect, usually it is very difficult to go in a direct manner. So, which is why we introduced two intermediate concepts. Nafis will be probably familiar with something similar we did in structural analysis, where we introduced two intermediate quantities in order to achieve this. But there we were talking about spatial derivatives. Because we had a flexible body, we were talking of spatial derivatives. So if we had the spatial derivatives of u and theta, we would end up with strains. Okay, first the deformation gradient and then the strains, and then we would relate it to the stress and eventually to the forces and moments. But here in dynamics, we are dealing with rigid body dynamics. So how it changes in terms of from a point to point is not of that much consequence as it is or in terms of how it changes with respect to time. So we will introduce two concepts which we have already done, in fact, as far as the translation is concerned, where we called it as the displacement, which is u dot, and the acceleration, which is u double dot. Okay, these are translational velocities and translational accelerations, as you recollect, and these are vectors as well. Okay, so this is your translational velocity, and this is your translational acceleration. So in a similar sense, in the end of last class, or actually towards the end, we introduced, remember, two more quantities, which we called as omega and alpha, which, as we pointed out over here on the top, is the angular velocity and the angular acceleration, right? And they were related to your theta, which is the rotation. And we talked about a simple situation of a 2D problem where we can think of it as a when the axis of rotation remains constant through a particular phase of the motion, and therefore we can call that without loss of generality as the k hat direction, and introduce, let's say, the polar coordinate or the natural coordinate or the Cartesian coordinate in the plane which is perpendicular to that, and we are essentially interested in what's happening in that plane of motion, right? So that is pretty much what we will do in today's class as well, every now and then. But we will also look at the 3D aspects of it. And when we meet next in person, after you, of course, finished with your homeworks, in case you're done by the end of tomorrow's class, maybe I will introduce certain specialized versions of what we do today, which is a 2D version of some of the 3D aspects that we will look at today. Okay. So once again, since I'm just mentioning the homework, I'd like to remind you what I mentioned at the end of your previous homework, that I really appreciate what you're putting up on the slides, but it is not a replacement for what you would do on your whiteboard. So I would really like you to use what you present in the slides primarily as a prop, and walk me through step by step the process of how you go about it, because I need to understand whether you are clearly aware of how you're going from point to point. So imagine uh, both my students and me to be learners in dynamics, and try to teach us, and of course your classmates as well, and try to teach us how we are solving a problem. So you don't skip any steps. You make state all the assumptions that you make at each step. Of course, draw the things that we have been always harping upon, namely your frame of reference, the coordinate system, or systems in plural, and of course the unit vectors. Okay, and make sure that whenever you're introducing these concepts, you and put them in equations. The left and right hand side are having the same dimensions, and they're also of the same kind of tensor. If left hand side is a scalar, right hand side also has to be a scalar. If left hand side is a vector, right hand side also has to be a vector. So please make sure of these things. And also when you're writing an integration, for example, putting the dx or a d theta with respect to which you're integrating, or a dt, all that is very, very critical. And if there are limits for the integration, specifying them, etc. Okay. When we're writing for ourselves, yes, it really doesn't matter. Maybe we might skip some steps, we might not follow the notation strictly, etc. But when we are expressing it to someone else, it's always good to write all this, so that all kinds of ambiguity are avoided, and things are very, very precise. Okay. Now, there are three parts to your next homework. Each part has four questions, except part B, I think, has only three questions. So I will give a very small derivation homework, which is just a 2 or 3 step derivation, so that you have four in each, and therefore it would be simple for you to divide it. And part C involves rolling. And that's a very, very simple concept. Again, something you would have learned in high school physics, but we will talk about it in a little more engaging manner, including vectors, etc., in today's class. So you'll be ready for part C as well. Okay. Of course, I assume some of you would have already ventured into it, but nonetheless, today's class will help you to do it in a more well-informed manner. Okay. Now, so far we have started from the effect, and we know that we can take the time derivatives of that. So whenever we take the time derivative, we need to mention that frame of reference. So it's the first time derivative, and you have to go from u or to omega. We have to take a time derivative again. So this is going from u and theta to u dot and w, which we'd of course also call as the velocity v and the acceleration a. Okay. And when we are doing these things, we also introduce the notations of the angular velocity of a particular body, let's say B, or an A if it's an aircraft, let's say, and in an inertial frame of reference or whatever frame of reference. It could be A in B or B in A or B in I or A in I. So whichever is the frame of reference comes on the left-hand side as a pre-superscript, and what is on the right-hand side is your post-superscript. Now, similar notation is there for this as well, I and B. So remember that we said that all these rotational motions are associated with the body. So you see that B and A or whatever you might use for the body is essentially referring to something which has a finite size. On the other hand, when you're looking at velocity on the top, you're essentially talking of a point, okay? And that point could be a center of mass, it could be particle, whatever, let's say P, and then that would also be with respect to a particular frame of reference, depending upon which frame of reference you have taken the derivative with respect to. The same thing holds for your acceleration also. So all these things, I want you to be very clear when you're writing out on the whiteboard, as well as if you're using any slides as props. I want you to be very, very clear about all of these notations that we have introduced and we continue to utilize, right? Now, so far, whatever we did in this portion and which we completed for the particle, and we will do that same for the rigid body today, is what we called as kinematics. So, in other words, uh, going directly from u and theta to F and M is tough, and which is why we introduced its derivatives, namely the first and the second derivatives, these four guys, which are the velocities and accelerations, both in translation and rotation. Okay, so these are the rotational accelerations, which we call, of course, as angular acceleration, and the angular velocity. Now, that is not sufficient, right? Now that we have come to U double dot or alpha and A, now we have these translational accelerations and rotational or angular accelerations. We have to relate that to F and M. Already you're familiar with relating the force to the acceleration. So you're familiar with relating these two, and we typically attribute that, of course, to Newton, and in particular, Newton's second law. Right. Now, we also would like to do a similar thing in relating our M and alpha, okay, which is an extension of Newton's second law, which is called as Euler's laws. We will see similarly it has a first and second denotation, which we will arrive at when we look at that in the slides. Now, it's not that people didn't know about this before Newton. In fact, your frames of reference, remember, I also mentioned, qualify it quite a few times as the inertial frame of reference, because IFOR, it's only under that situation, as you know, where the Newton's second law is valid, and therefore Euler's second law also, because Euler's laws are derived from Newton's second laws, which are valid only for particles, though Newton did apply it for bodies, which he considered as rigid, namely the planetary bodies, for example, the Earth, Sun, etc. For example, the Newton's law of universal law of gravitation that you see, Gmm divided by the distance squared between them as the force due to gravity. That is essentially dealing with finite sized bodies, right? The sun and the earth are not particles. But for this purpose, he assumed them to be particles, or in other words, all of their mass, capital M, that is the uppercase m, and the lowercase m, being concentrated at 2 points, which are essentially the centers of mass of these Earth and the Sun, for example, or for any two planetary bodies or satellites. Now, on the other hand, Euler went a step further and looked at not only forces but also moments, and therefore the rotations that are possible. And in fact, the planetary bodies, remember, are also rotating. Okay, the Earth is rotating about its own axis. In fact, the Sun is also moving as part of the solar system. The entire Sun is moving, and then there is motion of the galaxies, etc. So, at least from the solar system point of view, the rotation of the Earth on its own axis and the revolution of the Earth around the Sun become very critical, and we will look at some of those aspects as well, because those are again relevant for flying vehicles rotating and also going in circular paths or curved paths around the Earth in its atmosphere, or for that matter, space vehicles either in orbit or transiting from one orbit to another when you're doing an orbital maneuver. So this particular thing, what we called as the inertial frame of reference, um, is also equivalently called as the Newtonian frame of reference, for obvious reasons that the Newton's laws are valid in that. So some books and literature might refer to this not as inertial but as Newtonian. So just be aware of that. But as I said, people knew about this before Newton and even in the West. So that is Galileo, and therefore this is also called as Galilean frame of reference. Okay, so don't be confused about these terminologies because they refer to the one and the same thing. All that they are saying is that this is non-accelerating and non-rotating. Okay, if either one of them or both occur, that is the frame of reference that you're using is either rotating or accelerating, or both rotating and accelerating, then the validity it comes to question of Newton's second law, and therefore of the Euler's laws, which we will introduce today as well. So all of these things that we're talking about here, Newton's laws, for example, will be what is the primary thing over here in the kinetics of the particles, and the Euler's laws become critical in the kinetics of the rigid body. Okay, so I just wanted to, even though we knew parts and parcel of the some of these things, I just wanted you to again revisit this bigger picture to make sure that you're aware of what we are looking at over here. So Galileo is, as far as people go, as far as the West is concerned, but I introduce you to one of the great works in um, the East, especially in India. Kanada Maharishi, and his work is entirely about, there are lots of things that he has done, but parts of what he has done is what we call as the Vaisheshika Shastra. Unlike English, the Sanskrit language is phonetic in nature, so that we typically write it in what is known as the Devanagari script. So there's only one way in which it can be pronounced. There's no ambiguity over there. Unlike in English, for example, different spellings could be interpreted differently by people who are not aware of the correct pronunciation of those words. So, which is why you see all those accents that I'm using, like in this, or lines over or above, etc. Those are essentially talking about particular ways of pronouncing, because I'm using the Latin alphabet in order to describe what is actually in the Devanagari script. So, as I said, we will not go into that, but just it's important for us to be aware of that, because this is like millennia before Newton, and therefore it's very, very critical that we give the appropriate credits to them, even though we may not know the language or be as conversant with those languages as we are with English today around the world. So coming back, so we will start venturing into this. Even before we go to that, these triple dots that I looked at is what a few more things that I need to do, especially so that you can be able to do your homework. It's not like new concepts, but examples of what we have already learned. We want to apply it to this specific situation. So that's the example that we will take up now. One example is of rolling. So while we are at that, maybe I'll just ask you a question. So any of you can distinguish between what we call as pure rolling versus slipping versus skidding? Okay. A lot of people interchangeably use slipping and skidding, but technically speaking, in dynamics, these are two different things. Okay, they're not exactly the same. Okay, so can any of you unmute your microphone and let me know what you understand by these? It's okay if you are not precise about it, just from your basic understanding. Please go ahead.
Oh, sorry, we weren't unmuted.
Yeah, Nafis, go ahead.
Okay, slipping means that there's no friction.
Rolling is when there is friction, and so you have translational and rotational motion.
Which term are you referring to, Nafis?
Rolling is where you have friction, and so you have both translational and rotational motion.
Okay. So all three are present.
I think slipping is just translational. It's purely translational.
And I'm guessing skidding is a mix of both, possibly.
What's that again, please?
I said, this is just a guess. I said skidding may be a mix of both.
Which is already here, right? So translation and rotation are there both. How do you distinguish pure rolling from skidding? Andrew?
My thought was that with rolling, there's like a, well, it must be, I guess there must be like a constant source of acceleration. Though I don't think that's right, because I don't think angular acceleration is constant, but there's like one component is constant in rolling versus skidding.
Okay.
I'm not.
Okay, thanks, Viti. Anybody else?
It's skidding that there's just rotational acceleration and no translational. Like when you skid out in the mud.
But there would have to be friction because for the rolling, but and well,
Okay, even though I'm just writing whatever you're saying, I'm not committing myself as to whether these are right or wrong. Even though I put those tick marks, it doesn't mean it's correct. I'm just saying that what one of you said, I think, Nafis, that there is friction, there is translation, and there is rotation. Okay, which is what those tick marks mean. Okay, but you're moving towards the right direction. You're bringing in the concepts of friction, your translation, and rotation, which is all of which are very critical in understanding the distinction between these two, or these three rather, and therefore we are moving in the right direction. So would anybody else like to further qualify these things or even change?
Can I, sir?
Yes, please go ahead, Najapa.
Pure rolling is the contact point is not changing at all. Point of contact between two surfaces is not changing at all.
Okay.
Slipping is the point of contact changes.
Okay.
Skidding is very similar to kind of boat going on a river, or
Okay, giving an
a kind of a
example.
plate which is slipping. Skating, kind of skating.
Okay.
Sorry, can you explain how for pure rolling the plane of contact isn't changing? Because if it's moving across the surface, then I'm imagining like a wheel rolling, then wouldn't the point on the wheel be changing and the point it's touching on the surface be changing?
Can you explain that, Najapa?
I couldn't get your question. If you can kindly.
So she's not very clear about this statement that you made, that the point of contact is unchanging. So she'd like clarification why it is unchanging, because she feels it is changing.
You have two gears rotating each other, like gears rotating, or for example, two rigid body. I mean, one plate on which a ball rolls. The point of contact on which the ball rolls, uh, mm, uh, is on the surface. That point of contact cannot move. That is rigid. That's a fixed point. Yes, sir is writing correctly. That point is fixed and the body will roll over. There is that the translation of that point cannot happen in pure rolling.
I'm sorry, it's still
Yeah,
don't.
Lalita. Yeah.
Okay, don't.
Maybe you can just explain to him once again, what is it that you are not comfortable with this statement?
Yeah, I understand what you just said. I kind of get that during the rolling, because of friction, it's fixed at one point as it's like going over. But what I don't understand, if it is pure rolling, then the ball is moving relative to the surface. If you have a plate and a ball's rolling on it, it's moving around on the plate. So how can you say the point of contact isn't changing when it's in different spots? Like it's literally in a different place. So, and also on the ball, there's like infinity points. And if you're rolling around, then the ball, like it's moving around on its own surface relative to the plate. So the point of contact is continually changing, no?
Do you follow that, Nanjapa?
Point of contact. Yes, sir. Point of contact between the two surfaces. If we take, let's say, the ball which is on the top of a plane surface, let us say point 1, P1 for the surface and P2 for the surface, P2 for the ball. P1 and P2 are in contact with each other. And at any given point of time, P2 cannot slip to P2, P1, P2 of the surface. Let us say there is another point of P2 on the right side of the surface. Yeah, like when it rolls, it takes another point of, yeah, when it rolls, it takes another point. P1, this P2 of this and P1 of this cannot translate in between.
So are we equating all of the points on each surface? We're saying every point on the ball, every point on the surface of the ball is P2 and every point on the surface of the plane is P1. Is that what we're doing?
Precisely.
Okay, got it. So then it would be the same thing for flipping. The reason why it changes is because relative to the surface, like the translational motion is not happening, so relative to the surface, the object is not moving. Or it
Yes,
should be moving, but it's not, so it changes.
yes.
And what I wanted to say, I wanted to throw in a more intuitive example for skidding. What I think of is like a car on a muddy road, and if you're stuck somewhere, then you'll be rotating your tire, like you'll rev the engine, and the tire rotates, but you have no translational motion because you're stuck there. So that's what I think of when I think of skidding.
I understood your question, but that comes to slipping and skidding and not pure rolling.
Sorry, what? Are you talking about my example or the
Yeah.
question? Or
Let's say a car's tire going on a muddy road, which is slippery. At that point of time, there is translation as well as rotation, both of them. And that is
no,
not pure rolling. That
I'm
is,
saying theoretically, if the car got stuck in the mud and you're moving the tires, but the car is not moving, then that would be skidding, correct?
yes.
Okay.
Okay, so we will come to more precisely establishing these things, but most of what Nanjapa has mentioned are absolutely right. So the confusion does come, Lalita, and you're not alone in this. Pretty much everybody who's introduced to this concept will definitely have this question because whenever we've been talking of points so far on a body, be it on this ball B or the surface S, let us say. We've been thinking of these points to be fixed on those bodies, right? So in other words, we think P1 and P2 are fixed in S and B respectively. But what we are talking of here is not a point of those bodies, but a point of contact or the contact point, right? When you're talking of the contact point, it in general, it can vary from one location on the body to another. So the same point P2 is now over here. And when it comes over here, it is this same P2, and this is your P1. So even though from the point of view of S, these are two different points, which are at a distance from each other, a finite distance from each other. The contact point itself is essentially what we're talking about is common to both these bodies, which are in touch with each other, which is what we call as contact, and therefore this motion is taking place. And here, as pretty much every one of you pointed out, there are two aspects to it. There's this B, which is rolling on S, and when B is rolling on S, there is a rotation involved. That is about B's axis, there is a rotation. I called it a ball, but it might as well be a cylinder, in which case there is a line contact going through the blackboard. But we can look at just a particular cross section of that, and once again, it just becomes a point. So if we are comfortable dealing with this from a ball point of view, we can extend the same concept for the cylinder or a tire or whatever as well. Okay. Though in reality, you don't have a point contact example when it's a tire, which is highly hyperelastic, which means it goes to very large strains, deformations. There's also a little bit of viscoelasticity involved because the heat is there, therefore fairly large complications are there, and you'll typically have a surface contact. Okay, let's not complicate that so much. Here we were talking of ideal circle or a circular object, either 2D, in which case it's a cylinder, or it could be 3D, in which case it's a sphere or a ball, and that is essentially moving, right? So the reason why we are qualifying this as pure uh, rolling is because these two aspects, namely the translation of the ball over the surface and its rotation over the surface, are related in a tightly integrated fashion so that neither of them exceeds the other in terms of its contribution to the overall motion. On the other hand, these two things that we're talking about, slipping and skidding, are where one of them exceeds the other. Okay, so in this case, translation, of course, some of you gave the extreme situation. Let me write new things in blue so that you know where I'm writing. So you said only, that is not right, but and you said no rotation, which is also not right, but nonetheless, there is a difference between these two. How much the translation is contributing and how much the rotation is contributing to the overall motion. In this case, we're essentially engaged in the center of mass because that's what has moved from one point to another point. So this is, let's say, at time t equal to 0, and this is at some time t, right? Now, the center of mass's motion, that is essentially your translation that is happening, is also having a translation under a rotation which is happening at the point of contact, right? Now, here the contribution from translation is greater than the contribution from the rotation, and here it is the opposite, that the contribution from the rotation is greater than the translation as far as skidding is concerned. Okay, so when either of these happens, either slipping or skidding, then you are essentially continuing to have roll. In other words, it's not that rotation has completely disappeared even in slipping, but just that its contribution to the overall motion is smaller in nature. Okay, so right now things might seem a little hazy because I'm talking more in a qualitative sense, using English for the description without getting into the mathematics of it. But we will get into the mathematics and things will become a little more clearer for you when we do that. But essentially, this is all that there is. And of course, good that some of you brought in the aspect of friction, which is playing a very critical role. If the friction is sufficient, then essentially rolling takes place. When the friction is not sufficient, one of these two possibilities are there. But this is example that is given typically of a ball rolling or even a tire rolling on a road, etc. Either the tire gets worn out, or let's say there is ice on the road, and therefore pure rolling is no longer possible. But even in the case of an aircraft, there is a concept of these things. For example, if an aircraft is making a coordinated turn, let's say it's going around a circle which is horizontal, so its altitude is not changing. Essentially, it's going like that. So it's very clear that if it's a finite radius circle that we are looking at, then obviously it has to have a yaw, okay, so that it goes towards not a straight line, but essentially making a circle. Okay, so but uh, later on you will see when you learn aircraft dynamics that this yaw cannot be given independently. There has to be an aileron deflection as well, which is similar to the banking that we do when we are going on a road which is having a turn, especially when you're having a steep turn. You will see that you need a lot more banking that you have to do. Now, when you're trying to do that, and if you don't do it appropriately, or let's say it's a novice pilot, not as talented as Tilak, let's say, then when he or she is doing that kind of a turn, they might either deflect the rudder too much, or they might deflect the rudder a little lesser, or sometimes they might deflect the rudder even in the opposite direction, what we call as the adverse yaw. Okay, so when any one of these things happens, it is not yawing as much as it needs to in order to complete this particular turn, and therefore, in such a situation, what you have is a yaw which is outside the path of that particular circle. So in other words, if it's traversing that circle, your nose is not pointing towards the circumference of that circle, but it is essentially tilted a little bit away or a little bit inside. And this is what is called as either slipping or it's called as skidding. Okay. So this is from an aircraft perspective. Okay. Actually, you look at it from this perspective, there's no contact that is involved, but the concepts are a similar extension. And at this point in time, the mathematics that we do, we will not be able to mathematically model this. But I just want you to be aware of, even for an aircraft which is actually in flying and not on the ground taxiing or whatever, even there, some of these concepts do exist. It's not directly translatable from what you see as an actual material contact to what is happening in terms of the actual rotations that are involved over there along with the translations. But essentially the physics and mathematics, there's some commonality over there, which is why the same terminology is used there as well. Okay, you might still have quite a few questions, but I would urge you to wait till we do a little bit of the a mathematical modeling of that, the simplest case of this same problem where we are having a ball rolling over a road. And then we will try to, once we are there, we will see if we still have doubts or questions. I will try to answer those. Okay, but before we get even into pure rolling and slipping, we will just very quickly get to what we were doing earlier. Able to see my slide, right? Just show me a thumbs up. Yeah, okay. Okay, so this is the last slide that I had before we dispersed in the previous class. And here, let me just rush through what we did. We had 2 points because whatever we are looking at it now will be applicable for your rolling and skidding or slipping as well. So therefore, just bear with me. These are more generic motions, but we will specialize that to rolling very shortly. Okay, so these are the 2 points, P and Q, which are fixed on or in or with respect to a rigid body A, which we introduced. And therefore, we could talk about the velocities and accelerations in any inertial frame of reference of these 2 points, namely velocity of P in I, velocity of Q in I are related to each other. And so in other words, if you had determined one of them, it's not necessary to go to first principles to derive the other. We can actually do it without having to do that, right? So the velocity and acceleration in I are related, and we have already shown that if we know if we know the velocity at Q, then we don't need to derive Vp from fundamentals, but we just have to add a term. And that term is not even having any derivatives. It's just a cross product that we saw, which is your angular velocity of that body, whichever body omega is fixed on. I mean, the P and Q are fixed on, namely in this case, the body A that we are talking about over here. So that body A in, of course, the inertial frame of reference that we have introduced over here, right? So similarly, of course, your P and Q, the velocities that we are talking about are in the inertial frame of reference. This is the more complete way of writing this particular equation. Whereas for the position vector, you don't need to mention the frame of reference because it's the same in every frame of reference going from point Q to point P. It's the same vector R. It's only when you take the derivatives of R with respect to time or any other scalar quantity, you have to mention the, which is why velocity, for example, is has to have the frame of reference. Okay, so this is something that we have already shown towards the end of last class. Now, The other thing that we also showed is that if we knew the acceleration of Q, oops, if we knew the acceleration of Q, let's say if we knew the acceleration of Q, oops, okay. Yeah, sorry for the delay. So suppose we knew the acceleration of point Q, once again, of course, in the inertial frame of reference, then we can get the acceleration of some other point P, which is also fixed on the same body A with respect to the same inertial frame I, just by adding two terms now. So we're not adding just one term like we did with the velocity, but we are adding two terms, and we introduced those two terms at the end of last class. One is involving an omega cross omega with an RQP. And I had a question about why this particular sign is plus, even though we know that this is actually centripetal, which is towards the center and therefore should have essentially a negative sign. And I asked you to kind of work it out, but in case you have not done that, let me just explain now. So this is essentially, you can think of Q as the point from which you're drawing the, let's say, a radial coordinate system. So this will be along ER hat, whereas let's say it's a simple rotation where you have this along K hat. Without loss of generality, we can always call the axis of rotation as K hat. So you can see that if you look at the cylindrical coordinate system, where you have ER, E theta, and K in that particular order, just like you have, let's say, I hat, J hat, and K hat in a Cartesian coordinate system. Remember that the corresponding unit vectors in the case of the cylindrical coordinate system are ER hat, E theta hat, and K hat again. And so just like we had I cross J giving you K, J cross K giving you I, and that cyclic order is there from going from this to this and to this. Whereas if you take a cross product in the opposite direction, let's say J cross I, then it becomes negative K instead of a positive K, right? Same thing holds in a cyclic manner for ER, E theta, and K. So now you see that the cross product that we are having within the brackets over here, this particular bracket, is nothing but I would like to use different colors, but just that I'm not sure if it will once again stop writing. So I'll continue with the same color. So what I'm talking about here is K hat crossed with ER hat. Of course, these are magnitudes. I'm just skipping that just to show you why that positive sign instead of negative over here, right? So now you see that you're going multiplying K with ER through a cross product, and therefore it is in the cyclic nature, and therefore this should give you an E theta, right? So this should be equal to E theta hat. Now again, this omega is also the same omega, and that's also along K hat without loss of generality. And now you're talking about Pen works. Okay. Eraser doesn't. Okay. So anyway, now we have a k cross e theta. And now you see that it is going in the reverse direction, and therefore you give a negative sign. So k cross e theta would result in a minus er hat. Okay, so which is therefore centripetal. Okay, which is this positive sign that you have will become negative because of this negative sign, and therefore you see that that's exactly what we used to have. And I also said that part of the Coriolis is contained within this, but that's not the entire Coriolis. There's also a part which is contained within this, so you don't see it explicitly in this particular case, which will involve an r dot and a theta dot. But nonetheless, going from Q to P, because whether it is a point Q or point P, the accelerations will involve in general, both these new terms that we have talked about, centripetal and Coriolis, just that we have to be careful in terms of the appropriate signs, the brackets, etc., to make sure that we are not algebraically messing up these terms. Are there any questions on this? Can I move forward? Okay. So the next thing, so knowing the acceleration of one point on the rigid body, namely your P, I can get to the acceleration of any other point, which in this case we are calling as Q, using, of course, the rigid body's angular velocity omega and the angular acceleration alpha. But very carefully, we should mention always that these are vectors and these are of A in I and of A in I again for the velocity, angular velocity. Okay. So then coming to the second term, I think I already mentioned this. So in terms of the centripetal and centrifugal, we already saw that what looked like a positive actually turned out to be negative. So that's fine. Okay. Now we want to specialize what we did in the previous slide, which was only for which was for any 3D body. Now to 2D. Oh. I don't know why this happens. Okay, so just bear with me. Yeah, do any of you know how to probably resolve this?
What's the problem?
When I'm trying to write with the pen on PowerPoint, it just vanishes. It's not staying. So if I remove my pencil, then it goes off. Try this again. Ah, good. Okay. I'll not change anything. I'll not mess it up. Okay. So we did what we did already was for 3D. Now we want to specialize that for 2D. Obviously, things are going to be much simpler, which is what we will look at here. So in other words, the same thing that we did on the previous slide and in the end of last class, namely 2 points fixed on the moving rigid body, namely P and Q. But now it's a 2-dimensional motion, so therefore I can bring in my omega along the k hat direction. In fact, that's something that I illustrated with my pen marks in the previous slide. Okay. Now for the 2D rigid body dynamics, the angular velocity omega of that body, whatever you're looking at, A or B in I, and the angular acceleration alpha of A in I, both are in the z direction. So in other words, they do not have a I hat or a j hat component, or for that matter, in a cylindrical coordinate system, they do not have a component along ER or E theta. They have components only along the k hat direction. On the other hand, if you're using an intrinsic coordinate system, so then the intrinsic coordinate system, remember, had the unit vectors T, E, N, the tangential, normal, and the binormal. Okay. So when you go to 2-dimensional motion, then EB, all these are hat because they are unit vectors. So EB hat takes on the role of your k hat. Okay. So in other words, that becomes the axis of rotation because essentially your torsion is equal to 0 and only the curvature is there and in the general case, and therefore that's something similar to what we do. Whereas if you have a Cartesian coordinate system, you're only having the I and j components, you're not having the k. If you're having the cylindrical coordinate system, once again, you're having ER and E theta, but not the k hat terms. So the position vector is, of course, in the xy plane or the r theta plane equivalently, or equivalently, it could be in the TN plane for the intrinsic coordinate system, the tangential and the normal, right? So all of these are different ways of dealing with 2D problems, okay? So even though on the slide I'll be illustrating it with respect to X and Y, it's valid whether you have the R theta or the TN system. So all of these are essentially talking about a 2D motion, right? So in other words, we're dropping off K hat in the first two and EB hat, which is the binormal, in the third, which because it's perpendicular to that plane in which the motion we are interested in, namely the xy plane. That would be your EB hat will become identical to K hat in that case. Okay, so rewriting the same expression that we had for velocity of one point with respect to the other, the only difference from what we did last time is in the way in which we are writing this particular term that you see over here. We are putting it as magnitude omega. Now this is a scalar quantity. This is the angular speed. So it's essentially the magnitude of the angular velocity. So the magnitude of the angular velocity omega, which is a vector, now we are calling it as omega as a scalar, and that's essentially what we are putting over here. Once again, of course, it's of A in I. And we are saying that it doesn't have I hat or j hat components. It has only a k hat component, which is what we are showing here. On the other hand, if you were using a intrinsic coordinate system, it would be written in terms of EB hat. Okay, so that's as far as the velocity is concerned. As far as the acceleration is concerned, we have two terms, and both of these involve either omega or alpha, and those are the terms that we are replacing with simpler expressions. Instead of a generic vector omega, we have omega times k hat, where omega is a scalar measured number or magnitude of the angular velocity called as angular speed. Similarly, the angular acceleration's magnitude is also something that is present only in the k hat direction, not in the I hat and j hat directions. And therefore, we are replacing the vector alpha by the scalar alpha multiplied by k hat. So now if you look at this, there are two omegas multiplying each other, which are scalar quantities, and therefore you have this omega squared that is coming up. And then, of course, you have RQP as it is. And I illustrated that in the previous slide using the R theta P system, R theta Z coordinate system. But whichever coordinate system you use, you will essentially end up with a negative and R will remain as it is. Okay. So we've already looked at it in what the pen markings that I did in the previous slide. So here we're not able to simplify it any further as of now, but we can do that once the actual points Q and P are specified, and then you know what is the vector R. But you can, without loss of generality, once again, you can take the position vector such that or introduce the coordinate system such that it's emanating from Q, the point whose information you already have, and therefore this will become along ER. So this can be thought of along being along ER. Of course, it will have a certain magnitude, which we can write as RQP, once again a scalar quantity, a distance from Q to P, and then you will see that K hat cross ER hat will result in a E theta hat. Okay. Yeah. Now we suppose we substitute the angular velocity and acceleration with respect to theta. We know that angular velocity is nothing but theta dot. We're talking of the magnitudes. Okay, so we're talking of the magnitude of angular velocity, and the magnitude of angular acceleration become theta dot and theta double dot because we are dealing with a 2D problem over here. All right. So it's only one particular rotation that we are interested in, which is about the k hat direction. So we just replace omega as theta dot and alpha as theta double dot. When we do that, it's quite straightforward to see that this is what we would get. I'm a little hesitating to clear the board because I might not be able to get the pen again. I have to go through all that process. So anyway, I hope this overwriting doesn't affect your understanding of this term. It's just RQP. Okay. So the only difference is we've brought in this theta dot over here instead of omega, because V doesn't, of course, depend on alpha. There's no theta double dot. But in the other expression, AP, that we will write next, you will see that there is this alpha as well, which is replaced by theta double dot. Okay. And this, of course, simplifies. And we now recognize this omega squared R, which we are familiar with writing in high school also, whether it's centripetal or centrifugal with the appropriate force, the signs, positive and negative, right? Are there any questions on this in terms of the final expressions we have for the velocity and the acceleration in 2D? Because it's just a simplified version of what we saw in the previous slide for 3D. It's all good? Okay. So now we come to what I was describing earlier in the situation of pure rolling that we're talking about. That pure rolling involves neither slipping nor skidding. Okay. And at that point in time, I already mentioned to you that rolling has some kind of a balance between translation and rotation. Now, remember, translation and rotation have two different dimensions. Translation, for example, as the SI unit of meters, rotation as the SI unit of radians. And therefore, I cannot say this is equal to that. But essentially, I'm saying the contribution of either one of them to a particular motion is in a balanced way. Then we call it as pure rolling. But once there is an imbalance where translation is dominant and rotation is either lesser or hardly contributing, then we call that as slipping. And on the other hand, the other way, namely the rotation is dominant and the translation is not contributing much, then we call that as the skidding. Okay. So when either of these are not happening, then you essentially have pure rolling where you have a balance between the two. Yet, so we're still talking in qualitative terms, but from the next slide onwards, we will introduce some math along with the schematics in order to understand this better. We'll take up the same example that you guys were discussing, namely the ball, which is rolling over a surface. And we take that contact point, which we remember when we were writing on the free-form blackboard. We were talking about it as P1 and P2 without any change. We are just calling that as P and P prime, because remember that it's just a single contact point. Either we think of it as being a part of the wheel, or we think of it as being part of the road or the surface on which this rotation or rolling is taking place. So it's essentially the same point that we're talking about, P and P prime, but we are thinking of it as belonging temporarily or instantaneously either to the wheel or to the road. And if it belongs to the wheel, we call it P. And if we see that it is belonging to the surface, then we call it as P prime. Okay. So as always, we introduce an inertial frame of reference. Okay. And all frames of reference and rigid bodies, we will use uppercase with a circle around them. Okay. So this is I. And then we introduce the coordinates X and Y, and we introduce the corresponding unit vectors I hat and J hat along this, right? So now there are other things that we like to introduce over here. One is the C, which is nothing but your center of mass, or in this particular case, assuming that this is a well-balanced wheel, you're looking at it from a geometric center, and therefore, and also let's say the mass distribution is axisymmetric, then you end up with, in this particular case, the center of mass and the centroid, or from the geometry point of view, the center of the circle. We are talking of the same thing in all these different terminology that we are using here, right? And as I said, if it's a sphere, you know that there is a single point of contact. But if it is, let's say, a cylinder, then you have a line contact, and that line contact will be, yeah, let me just see. So that line contact, because we are looking at just a cross section of that, that also it just becomes any particular point on that line, and therefore we are dealing with just these 2 points. Another quantity that we like to introduce, obviously of great significance here, is the rotational speed theta dot. It is essentially a 2D motion, so it's only a theta dot, which is along your k hat, which is of course coming out of the black board that you see over here, which is your k hat, right? So your theta dot is about k hat. But if you look at the way I've drawn theta dot over here, because I want motion along the positive I direction of the center of mass, I've drawn it in the clockwise. Okay, so which means that if I use the right hand thumb rule, so essentially this is going into the board, and therefore it's along the negative k hat direction, and therefore it should be minus theta dot k hat is the angular velocity of this particular body, which is rolling over the surface, okay, with or without slipping. Okay. So now we consider these 2 rigid bodies. So in other words, the surface is also a rigid body. Okay. So the surface could be a boundary, it could be a surface, it could be a massless entity that we are thinking. Remember, I also talked about the skidding and slipping of an aircraft as well when making a coordinated turn, right? So it could be just a boundary or surface, and that we are quite familiar with when we introduce the frame of reference. We said it could be a rigid body, it could be a fictitious entity, which is a massless rigid body as well. It doesn't matter. You just because all of our relations are subjective, we need to essentially have some kind of an anchor, and that anchor happens to be the frame of reference. Okay. And it's important to recognize that we are talking of a continuous contact over here. Should try to resolve this next time. See why this is happening again and again. Lost it anyway. Oh, okay. I can write with my hand. Hello, writing with the hand. Okay. So another Microsoft versus Apple thing, I guess. So let's. Okay, then I'll not be able to change the. Okay. So we have introduced all the terms over there, the new variables that we have, the points, the body, and the speeds that are involved. And we said that we have these two rigid bodies. The second may be a boundary or surface in continuous contact. Now, to answer Lalita's question, which pretty much Nanjapa explained quite well, essentially we're talking of a instantaneous contact point, which is neither belonging to the ball or to the surface on which the ball is rolling over. So essentially that point itself is changing in both of these bodies, okay? But what we are interested in is that contact point that we are following. This is somewhat similar to the kind of dynamics that I described to you in with the very first class, the Lagrangian and Eulerian. In one case, you follow a material point. In the other case, you are essentially looking at a particular location and essentially seeing anything which is traversing past it. So it's something similar to that. The contact point uh, taken from the point of view of the any of the bodies that are involved is actually changing. But uh, we are interested in the contact mechanics there without going into too much of details of contact mechanics because it's a separate subject and study by itself. You could have multiple courses on contact mechanics, but we are taking only one aspect of that, which is the point of contact and what actually happens there. So there is an instantaneous contact of a particular pair of points, which we are calling as P and P prime. Truly speaking, this is a single point, but if we imagine it to be a part of the ball, we call it P. If we imagine it to be a part of the surface, we call it P prime. Okay, so the two rigid bodies that we are dealing with. So then, if you're talking of rolling, so then essentially there's a zero relative velocity. So this is what Najapa alluded to, that there is no relative motion. So instantaneously, there is a zero relative velocity between the paired contact points. So that is the pair that we are talking of now is P in the body and P prime on the surface. And therefore, this particular point, actually a single point, but thought of, imagined to be two different distinct points, is essentially not having any velocity with respect to each other. So in other words, what we are looking at over here is uh, again attempt. Okay, it doesn't work. Okay. Anyway, what I was trying to. Okay, let me just talk about it. Okay. The rolling that is happening is zero relative velocity between the two contact points, P and P prime. On the other hand, if you're looking at slipping, there is a non-zero relative velocity between them. And here is where the translation dominates over uh, over the rotation. Okay. On the other hand, if it is skidding also, you will have a non-zero relative velocity, but it would be negative because you would have the rotation, which is dominating over the translation. Okay. Once again, we are still talking in terms of explaining it, but not in terms of the actual equations, which we'll come to in this slide. Now for single rigid body, rolling on a non-moving surface, because we can bring in other complications here. We're looking at a horizontal surface. It's not inclined, neither is the surface itself moving. So we're keeping this not only the surface horizontal, but we're not allowing it to move. We are only moving the ball or the cylinder. And for a single rigid body, which is rolling on a non-moving surface, you can see that rolling essentially means that zero velocity of the surface contact points, just specializing what we talked about in the previous slide. So the actual contact point, though, can be changing with time. It is this which causes the confusion, like what Lalita was alluding to. So as long as we are aware that P is not fixed on the ball or the cylinder, then we can see that what we are actually talking about. So it's a different point on the cylinder, which is now we will be tracking at a different instant in time. So it changes with time, the actual contact point, both in the ball as well as in the on the surface, as long as you're having rolling. So, but zero instant in, yeah, go ahead.
I'm curious to know, like, in which reference frame are we saying that there's like
So-
zero velocity of the contact?
So it's the reference frame that we have introduced. That is this I that we're talking about.
Okay.
Yeah.
Okay.
No, I'm sorry. They're talking of the relative velocity between P and P prime. Okay.
Yes.
So if you're talking of the velocity of P, then it is with respect to the surface, because P is a part of the cylinder. And if you're talking of the relative velocity of P prime with respect to P, it is the frame of reference is the cylinder. Is that clear? So I take back what I said just before that it is the inertial frame of reference. It's not. Okay. So is that clear?
Yes. So when we're making the statement that
Yeah.
zero velocity of the surface contact point,
Mhm.
does that refer, which one does that refer to?
Okay. It really doesn't matter. See, because what can't see if I'm able to, or maybe I should be able to write with my hands if I'm not able to write with this. Yeah. Okay. Then also writes. So now, so the speeds that we are talking about, remember, is VP. Oh, maybe because I'm writing outside this surface. Okay, let me see. Okay, what's this? Okay, pardon my handwriting with my finger. So this is S that we are talking about, the surface, and B that we are talking about. So P is part of B and P prime is part of S. So if you're looking at the velocity of P in B, that is equal to 0. Okay.
Yes.
But if you're talking of the, similarly, if you're talking of the velocity of P prime in S, that is equal to 0, which is what we mean by these 2 points are fixed in those respective bodies, P in B and P prime in S. Okay. But what we are talking about now is the relative velocity. And so for that, it's okay for you to take it with respect to this inertial frame of reference, I. Okay. So I can talk of IV P prime and an IVP. So I'm essentially saying that these two are equal to each other. So in other words, there's no relative velocity between them.
Okay.
So P is not moving with respect to P prime. P prime is not moving with respect to P. But this could, in general, both of them, of course, could be non-zero. And in fact, they are, because this is moving around, right?
Right. Okay.
Okay.
Thank you.
Welcome. Okay, so the actual contact point may be changing with respect to time, but zero instantaneous velocity of the current contact point. Okay, so in other words, what was in contact some time ago would now be somewhere over here, right? And so this particular contact would be at some minus T naught. Okay. I'm sorry. I'll figure this out some time later. Okay. So now what we're talking about is there are the actual contact point at different times, let's say minus T naught and plus T naught would be on the left side or the right side. Maybe, let's see if I can at least I can use the laser pointer, I guess. Yeah. Yeah. So at the current instant of time, P and P prime are over here, but as far as the body is concerned, at some instant of time negative, which is let's say minus T naught, it would have been over here on this and over here on this. At some positive time, it would be over here on the body, which is rotating, rolling, and it would be somewhere over here as far as the surface is concerned. So with respect to the either of the bodies, these points are actually moving. So it's not that these points are fixed on those things. It's just the contact point that we are talking about. Again, both of them are exactly identical, just that imaginatively we are distinguishing these two as P and P prime, which is of course why, because in reality they are the same. That's why you have the zero instantaneous velocity of the current contact point. Okay, now we will recollect that thing that we just introduced, the 2 points fixed on the moving rigid body, and we will apply it to this particular problem, right? So it's the same equation that I'm writing from before, so I'll not explain it to you. Again, in terms of the acceleration also, so it's the whole slide that I'm repeating from the end of last class as well as the beginning of today's class, okay? Now, let's look at this as a wheel on a fixed straight line, which is what we've been dealing with earlier as well. And without loss of any generality, I can move this XY axis wherever I want. Okay, so we can translate that. It's only the origin which will move. I'm not rotating the XY axis. I'm just moving from where I had drawn it earlier over here. Remember, from I had drawn with the origin over here. Doesn't matter if I shift the origin here. The translations of reference surfaces do not, or the frames of reference do not matter. Okay. So once again, that point, we call it as C, the center of mass, which also in this case happens to be the centroid or the center of the circle, and the same theta dot we have for the angular speed. Okay, so now again, without loss of generality, we can always take the axis of rotation as k hat, because that's how we introduce our x and y axis, the coordinates, and also the I hat and j hat parallel to them. Therefore, I can treat the angular velocity as being along k hat direction, and because I'm showing it in the clockwise direction, therefore I have a negative sign both in the angular velocity as well as the angular acceleration, because they are along minus k hat. And of course, the magnitude of that becomes theta dot and theta double dot, because there's only one rotation that is involved, and its time derivative, the scalar quantity's time derivative that we are looking at. Now coming to the wheel center, which is your C that you see here. The wheel centers having a velocity and acceleration, which we will denote as VC and AC. This is with respect to the inertial frame in which X, Y, I, and J are fixed. So this is VC is just going to be XC hat, I hat. In other words, it's not a bumpy ride where C is going up and down, or for that matter, if it is a tire, in which case it takes some of those rough movements and takes care of that. So all of that is ignored over here. It's just saying that C is moving only along the x-axis doesn't have a y component. Okay, and again, it's a 2D motion, so obviously doesn't have a z component. So velocity is only of c is only along I hat. So is the acceleration, and the only position change that c is having is in the x direction, and which we call as x subscript c to denote that it is of the point c, and therefore the velocity is xc dot, and the acceleration is xc double dot in terms of its magnitude, the direction being I hat. Okay, so once again, you can recognize that I'm talking about, when I'm talking about omega and alpha, which are angular quantities, namely angular velocity and angular acceleration, it's of a body. That is, I'm talking of a wheel. On the other hand, when I'm talking of velocity and acceleration, which is translational, not angular, then I'm talking of a point, not of the wheel. I'm talking of a particular point on the wheel, which is the center of mass. So always have this distinction between angular quantities and translational quantities, and that is omega and alpha on the one hand, and b and a on the other hand. These are dealing with a body, and this is dealing with a point. Okay. So now we have very simplified expressions for all of these under the assumptions that we've been stating as we move forward. Now, yeah, this is something that I just stated, that the rigid body has angular velocity and angular acceleration, while the point has a velocity and acceleration. It's not never the other way around. So the default units of angle in any engineering formula or calculation, is the radian, though we can, of course, express angles in other units like degrees, minutes, and seconds, etc. We can always convert from one to the other as pi radians equal to 180 degrees. And when nothing is mentioned, which is what we mean by default, of course, it's radians. Okay, which is of course valid for your thetas that we talked about here, and the derivatives of theta as well. So this will be in radians per second or radian per second squared, depending upon whether it's omega or alpha. So the rolling wheel is on a fixed straight line, the same problem that we are continuing with in this slide as well. Now we introduce the so-called rolling constraint, which is no slip or no skid. And that constraint is essentially that VP equal to 0. Okay, so if VP is positive, then translation dominates. And then we are talking about the slip. And if VP is negative, we are talking of skid. Okay, whereas pure rolling, we have VP equal to 0. So the rolling constraint relates the center of mass's velocity to the wheel's angular velocity. So because of this condition that we have, the rolling constraint, we can utilize that to correlate what we have introduced, namely theta dot and xc dot. So whatever we had in the previous slide, remember, you're talking of the velocity and acceleration of c as xc dot and xc double dot, the magnitudes, both along the I direction, I hat, and theta dot and theta double dot being omega and alpha, which are both along k hat, which is perpendicular to both I hat and j hat. So now, because of that, we see that your xc dot is now equal to r theta dot, because now you can think of it as something which this body is rotating about p, even though it's actually rotating about c, it's about p because these are 2 points that we are having instantaneously fixed on this particular rigid body, because P we are thinking as being a part of the wheel, and C being a part of the wheel as well. And therefore, when I utilize that, I will see that your xc dot is equal to r theta dot. Okay, that is consistent with your VP being equal to 0. So now your the velocity of the center of mass is therefore, remember that in the previous slide we had it as xc dot times I hat. Now we can write it in terms of theta by bringing in xc dot as r theta dot, which is what we do here. And because this is true, and I take the derivative of this, and the radius r, though I've written small r, it's actually the radius of this cylinder or ball, which is a constant because we're dealing with a rigid body. On the other hand, if you had an actual tire, there could be a small change in the R because of the flexibility of the tire. Here you can think of it, let's say, like a metallic wheel. Even there, in fact, we will have a very small, much smaller than the actual rubber-based tires. but nonetheless, it will be much lesser. Okay, but in reality, even though you might have a flexible body, here we are dealing only with rigid body dynamics, and therefore this just becomes r theta double dot along I hat. Are there any questions on the slide? Okay, let me move forward then. So the integration, of course, these are differential equations because they involve a d by dt, and no unit vector needs to be specified because it's a scalar quantity. It's a magnitude theta of the rotation that is involved in both these cases, one as a d by dt and the other as d squared by dt squared. Again, ordinary derivatives because t is the only independent variable that is involved. Coming to the constraint, if we want to integrate this particular equation, xc dot equal to r theta dot, then obviously you get xc equal to r theta along with the integration constant, and that integration constant can be solved by uh, agreeing to what we deal with as at what value of theta xc is 0. So it's essentially fixing some point as a starting point for this rolling to take place. So it really doesn't matter from the problem perspective because what we are interested is only in xc dot and then xc double dot, in which case the constants derivatives with respect to time will vanish. Only this will remain, which is what you see over here and here too. And in fact, we would not even need the velocity any further when we get into the kinetics. It's only the accelerations that will be needed along with the instead of mass, we'll have inertia, and then we will be dealing with the angular velocities and the angular accelerations. So the angular acceleration will be associated, namely theta double dot will be associated with a particular moment of inertia. So we'll introduce those like concepts of kinetics later on. For tomorrow's homework, there's no problem related to kinetics. It's only kinematics of the rolling. We will revisit rolling to take it further when we get into the kinetics, where you'll have a few more problems in future problem sets. So this is as far as today's class is concerned. Let me see if I have. Yeah, maybe I can finish with this because I said that there are actually total of 11 questions because even though part A and part C have 4 questions each, part B has only 3 questions in your current homework that you will present tomorrow, homework number 4. And therefore, in view of that, I just want to give this because remember in the previous slide, what I had derived is the acceleration of C in the inertial frame of reference. So AC and I is what I had. Okay. But I want to get to the acceleration of P. I have said that the velocity of P equal to 0, but that's only an instantaneous velocity. Okay. So in other words, the velocity of P at just an instant before or just an instant later from the instant of interest for us can be non-zero, which means that there is a change in velocity with time, which means there is a change in, which means there is a non-zero acceleration of this point P as well. But what we talked about over here is just the acceleration of the center of mass alone. So what I would like you to do is to utilize the formula that we already have for 2 points on the rigid body, because both P and C instantaneously can be thought to be a part of the same rigid body. And using that and using the value for AC that we had in the previous slide, I want you to get to AP. And you'll see that this turns out to be R theta dot squared J hat, very different from what we had here. Remember, it is r theta double dot I hat. So it's not only the magnitude which is different, but also the direction is different. The acceleration of C is along the x-axis, which is along I hat. On the other hand, the acceleration of P, this particular point that you see over here, is along J hat, that is in the vertical direction, that is having an r theta dot squared, which you're again very familiar with what it typically means. So going from AC to AP is what I want one of you to deal with as as the missing fourth question in part B. Okay, so with this, I'll conclude today's class. Let me know if you have any questions. I'd be most happy to answer. Okay, if there are no questions, let's disperse and meet in person tomorrow. See you then.
Thank you.
Welcome.
Thank you, sir.
Most welcome, Ranjana.